그리고 소리는 이쪽으로.
이번 이제 슬라이드 쇼를 한번 시작해 보시죠. 네.
선생님 혹시 마스크를 계속 끼고 계셔야 되나요?
저희가 끼고 있을 테니까
네.
벗고 하실 때는 시작해도 되나? 네. 하시고. 자, 시작하도록 하겠습니다. 네, 오늘 세 번째 콜로퀴움 연사를 소개해드리겠습니다. UC 산타바바라에 최근에 부임하셨습니다. 네, 소개를 해주실 것 같고요. 네, 정혜원 교수님 소개해드리고요. 지금 산타바바라에 ECE에 교수 재직 중이시고, 네, 학부는 카이스트 2014년 졸업하시고, 그 다음에 석사하고 박사는 CMU EC에서 협의를 하셨습니다. 펄틱 글로벌
네.
교수님과 맞으시죠?
맞아요.
이미 글로벌 교수님이 지도했고, 그 다음에 이제 20년부터 22년까지 하버드에서 포스트하고 있었습니다. 그리고 연구 분야는 정보 이론, 분산 커뮤니케이팅, 머신러닝, AI 윤리 관련해서 연구를 많이 하고 계시고, 오늘은 AI 페어니스 쪽 관련해서 최신 연구 결과를 해주실 테니까 재밌게 들어보면 좋을 것 같습니다. 자, 모두 박수로 기다려주시기 바랍니다.
네. 이렇게 초대해 주시고 소개 잘 해주셔서 너무 감사드리고요. 제가 발표는 사실 영어로 할 건데 혹시 중간에 질문 있으시면 한국말로 질문하셔도 상관없으시고요. 네. 그리고 좀 인포멀하게 혹시 중간에 질문 있으시면 아무 때나 질문해 주시면 좀 좋을 것 같아요. Okay, so I'm really excited and honored to be here today. And I'll talk about fair machine learning in application to education. And I'll tell you about how we can use an information theorist perspective for fair machine learning. So these are snapshots of students protesting against A-levels grading algorithm in the UK. And the A-levels are the college entrance exam in the UK, like SUMON. And in 2020, this exam could not happen in person because of COVID. So the government decided to use an algorithm to assign grades to students instead. But it turned out that this algorithm systematically assigned lower grades to historically low performing schools at low resource areas and assigned high grades to historically high performing schools in the wealthy area. So this discriminatory performance of this algorithm sparked nationwide rage and protest, and the grades assigned by the algorithm had to be retracted at the end. And this is not the only example of algorithms showing bias and discrimination. This is a famous example of using algorithm to do recidivism prediction. So in this example, we want to use an algorithm to decide whether we want to release a criminal earlier or later, depending on the probability of committing them committing the crime again. And it turned out that this algorithm released more white criminals than black criminals. So black criminals have to stay in the prison longer than white criminals. And other examples, other well-known examples are online ads recommend different ads to different genders or different races. For example, it's going to show more high-income jobs to males than females. And another example is facial recognition algorithm that performs really well on white males, but it doesn't perform as well on other race or gender. So if you look at these examples, you'll feel like, oh, this is not right. This is upsetting. We have to solve these problems, right? But I want to give you a more concrete view of why we should care about these problems of ethical machine learning and why now. So this graph is a little outdated. It's until 2017. I didn't find a cute graph like this that comes all the way until 2022. But you can see that the number of papers on fairness in machine learning has been growing almost exponentially until 2017. And to reflect this trend, there have been new conferences, especially on this topic, such as ACM Fact or AIES. And at major machine learning conferences like NeurIPS or ICML or CDPR, there have been a lot of workshops on exactly this topic of ethical or fair machine learning. So why do we care about this problem all of a sudden? So this is what I think. So machine learning has been entering sectors, critical sectors like finance, education, or legal sector, or government administration, or medicine, or self-driving, where usually people have been making important decisions. And now we want to use machine learning algorithms to make those human-related decisions. But for machines to completely replace humans, there's an important bottleneck, which is that the general public is often very distrusting of the algorithm-based decisions. So it is crucial to build an algorithm that is not just accurate, but also trustworthy. And to build algorithms that we humans can trust, it is important for the algorithm to respect the same moral values we humans respect and we humans agree upon as a society, right? And some people think that this is a last mile problem because even if the technology itself is 99% mature, if these things are not satisfied, the technology will not be adopted in practice. So it might be debatable whether we are just a mile away from machine learning taking over these important sectors, or 2 miles away, or 10 miles away. But I think we all agree that this is coming very soon, and the problem of ethical machine learning is an imminent problem. So then what are those moral values we have to care about? So this is a slide I borrowed from Alexandra Chuletova, who's a prominent researcher in this field. And I really like this definition of organizational justice. So this was defined by Colloquium in 2001, and he defined 4 different kinds of justice for organizational justice. The first one is distributed justice, which is perceived fairness of the decisions or outcomes. So whether the algorithm is giving like fair and even distribution to people. And procedural justice is a little different. It's perceived fairness of the process that produce the decisions and outcomes. So even if the outcome itself is fair, if the procedure that reach those decisions are not fair, then people might not feel that the process was fair. So for instance, we want the process to reflect our input, and if we feel like the decision was unfair, we want there to be some way to contest the results and change the results and so on. And another pillar of organizational justice is informational justice, which means that sufficiency and completeness of information provided to explain and justify decisions and outcomes. So whether the decision-making entity is giving truthful and transparent information about the process. And the last one is interpersonal justice, which means extent to which people are treated with dignity and respect by those making and communicating decisions. So because interpersonal justice is basically about interpersonal interaction. It doesn't have direct relation to machine learning algorithms, but for all the other three justice types, I think they have direct connection to machine learning algorithms. And so distributive justice is related to algorithmic fairness, which cares about whether the algorithm is doing fair and even distribution to people. And procedural justice is related to accountability of algorithms and algorithmic recourse. And informational justice will be related to explainability of machine learning algorithms. And in this talk, even though all of these are really, really important problems, I'll focus on algorithmic fairness part of the justice. So when I say fairness in machine learning, first question people ask is, and how do you define fairness in machine learning? How do you even define that mathematically? So there have been a lot of different definitions of fairness, but in big picture, there are usually two different categories. First one is group fairness, and the second one is individual fairness. So let me begin with group fairness. So to define group fairness, there should be a group attribute S. For instance, S equals 0 can be a minority group such as female, and S equals 1 can be majority group such as male. And let's just for the sake of explanation, let's assume that we have binary prediction Y hat. And the basic idea of group fairness is that the performance of a machine learning model should not depend on sensitive group attribute S, which means that regardless of your gender or regardless of your race, machine learning models should perform equally well. And depending on how we define performance, there are many different definitions of group fairness measures. For instance, if we care about the rate of people getting positive prediction, and if you want to make sure that this positive rate is equal across groups, then that definition is statistical parity. Or if we care more about having high true positive rate or low false negative rate, then that definition is equalized opportunity. Or if we want to have equal accuracy across groups, then the fairness measure is called accuracy parity. And ideally, we want these metrics to be exactly the same across all the groups, but that's usually not possible in reality. So what we want is the difference in these metrics, given the group attribute S, to be as small as possible. And another class of fairness definition is individual fairness. And this does not require any group attributes. Basically, what this says is that if two individuals are very similar, so let's get rid of all the sensitive attributes like race or gender that are not related to the decision we want to make. So let's just have those relevant features. And if two people are very similar in those relevant features, then they have to get similar treatment. But one big drawback of individual fairness is that we have to have some kind of metric to measure the similarity between two people, and that is very application dependent, and it's not always straightforward to define that distance metric. So in practice, people usually use group fairness metric, and that's what I'm going to use in this talk as well. Any questions so far? Yes.
제가 최근에 읽었던 논문 중에 페어니스를 특정한 메트릭을 구성하기 위해서 이제 평균 버크스를 조금 더 많이 떨어뜨리고 이제 페어한 쪽에 대해서 버크스를 조금 떨어뜨리는 식으로 해서 이제 저런 메트릭을 맞추는 경우가 많다고 또 한쪽에서는 오히려 이제 성능이 안 나오는 쪽을 안 나오는 그룹에 대해서 부스트하는 쪽이 있다고 들었는데 그 페어적인 면에서 혹시 어느 쪽이 더 중요한지.
Maybe for the audience online, could you repeat the question?
Oh, okay, so the question was that to make the algorithm fair, there are two different ways to make it fair. If you have one group that has low performance, you can try to boost that group's performance, or in another case, you can try to reduce the performance of the high performing group. And which way, better way in terms of fairness? That was your question, right? Right. That's a great question. I don't think I have like a concrete answer to that question, but so in general, fairness research is trade-off of accuracy, the overall performance, and fairness. So there's always trade-off between how fair we can make the model, and how accurate we can predict overall. Because if we just build a model that just gives the same prediction to everyone, just gives 0 to everyone, then that is fair, right? But then if you think about the performance of the model, that's really poor. So ideally what we want is as good fairness as possible and as accurate as possible model. And I'm going to talk a little bit more about that in the second section of my talk as well. Any other questions? Okay. All right. So now we've set up what fairness is in machine learning. I just want to give a few words on how information theory can help to build fair machine learning algorithms. So John von Neumann and Claude Shannon, early fathers of our digital technology, they developed information theoretic tools to build reliable computing and communication systems in 1950s, because in the 50s, those computers made of vacuum tubes or radio communication systems suffered from a lot of unreliability issues. But these technologies have evolved a lot, and in 2022, these individual technologies have become extremely reliable. But now we have different reliability challenges in 2022, and I view reliability challenges in two different metrics. First one is reliability challenges in machine metrics, such as accuracy or computation time. And even though individual chips like CPUs and GPUs are made really reliable, now that we're using thousands and millions of them together to run large-scale computations, large-scale machine learning training, there are new challenges in machine metrics. And another challenge is reliability challenges in human metrics, because as we saw, even if the algorithm is really accurate or really fast, if it doesn't satisfy soft qualities like fairness, accountability, or explainability, people cannot really rely on or trust the algorithm. So these reliability challenges now manifest in different ways in 2022, but the fundamental concepts and tools in information theory that were built to design reliable systems can be adapted and applied in 2022. Furthermore, to me, information theory is not just a set of tools, it's a way of thinking. And this is how I view information theoretic blueprints. So we usually start with a problem, such as, oh, this algorithm has different performance for different races. And the first thing we do as an information theorist is to come up with a simple model that abstracts away minute details. And we establish a simple and analyzable mathematical model. And then we do some kind of mathematical analysis, deriving different ideas from statistics, probability theory, optimization, or discrete math, and etc. And then these results are actually useful in practice because it gives us fundamental operational limits and guidelines on how to design an algorithm that meets the fundamental limit. So in this talk, I'm going to have 3 different parts if I have enough time. So in the first part, I am going to talk about more data science project that reveals the fairness risk of applying machine learning in math education. And this work has been presented at several workshops in machine learning for education related workshops. And it's a joint work with Michael, Nilanjana, Miri, and Flavio. And the second and third part of the talk, I'll tell you more about method research to build fair algorithms. So let's get into the first part. So machine learning has already entered our education system. For example, there are AI textbooks that give you personalized educational content. And also there are many AI-based grading systems. And also there are AI chatbots on university or like school websites that guide you through the school website. But as we saw, these machine learning used in education have faced a lot of public backlash, as we saw in the A-level exams example. And another example is UT Austin. They tried to use machine learning based admission system to filter through a lot of applications. And it turned out that this algorithm perpetuated the existing bias, so they had to phase out the algorithm in the end. So in this work, what we want to do is we want to understand the fairness risk by using a case study with a realistic example scenario. And what we want to do is we have two real-world data sets, middle school and high school data sets that contain student past performance and students and parents survey, and it contains thousands of student data from the US. And we want to train vanilla or off-the-shelf machine learning algorithms to do the future performance prediction. So we want to predict students' future math performance, whether they're going to be in the top 50% or the bottom 50%. So this is a binary prediction problem. And especially what we want to understand is if the algorithm shows any kind of racial bias. And to show this, we group races into two groups. First one is white and Asian students, and the second one is Black, Hispanic, Native American students. And in the US, white and Asian students are thought of as majority group in terms of STEM education, so we do this grouping. And before I show the results of training machine learning algorithms here, I just want to give you the context of what different errors mean in this particular application using this confusion matrix. So false negative error here means the student actually performs well in the future, but the machine learning algorithm gives negative predictions. So the algorithm is giving pessimistic underestimation to students. And on the other hand, false positive means the student performs poorly in the future, but it gets positive prediction from the algorithm. So the algorithm is kind of giving the benefit of the doubt to the student. And accuracy is usually the metric of merit we use when we want to decide which model to use. And accuracy measures the aggregate of false positive and false negative errors. Now, keeping this in mind, now I'm going to show you the results of training random forest on middle school and high school data set. And now let's look at the results. First thing I want you to look at is the accuracy between white Asian students and Black, Hispanic, Native American students. And then you'll notice that the difference in accuracy is very small between the two groups. But if you look below accuracy and look how they are misclassified, it's very different. So if you look at false positive rate, you can see that in both middle school and high school data sets, white and Asian students have much higher false positive rates, while Black, Hispanic, and Native American students have much higher false negative rates. So what this shows is that accuracies are very similar for both groups, but how they are misclassified is very different. White and Asian students are getting all the benefit of the doubt, while Black, Hispanic, Native American students are getting pessimistic underestimation. So to put this in the fair machine learning language, what this is saying is that in terms of accuracy parity, this random forest model performs pretty well. But if you look at equalized opportunity or equalized odds metrics, then it performs really poorly. And this actually has a strong implication on students. So that's what I'm going to talk about briefly. So let's think about a scenario where we use this random forest model. to do class placement for 8th grade students to Algebra 1 class. So Algebra 1 is thought of as gatekeeper course in American education system. Because if you perform well in Algebra 1, then it's more likely that you'll continue more advanced science and math education. And if you struggle with Algebra 1, it's more likely that you're just going to give up science and math overall and do something different. And also the research shows that when students take Algebra 1 matters, and whether the student takes algebra in their 8th grade is a strong predictor of their success in STEM education. So now let's look at who's taking Algebra 1 in their 8th grade. So if you look at the statistics, you can see that there's a lot more Asian and white students taking Algebra 1 in 8th grade compared to Hispanic, Native American, or Black students. Then if you use this algorithm to decide whether we're gonna put this student in more advanced Algebra 1 class in their 8th grade or more basic class in their 8th grade, what it's gonna do is it's gonna perpetuate this trend we already have in the society, and Black, Hispanic, and Native American students can lose the opportunity for the early access to Algebra 1 because the algorithm is assigning pessimistic underestimation to them and is giving more benefit of the doubt and more opportunity to white and Asian students. And furthermore, this puts minority students at higher risk of losing interest in STEM because in educational psychology, it was shown that negatively stereotyped groups, they can more easily, they can lose interest in STEM fields more easily when they receive lower grades or pessimistic underestimation because it consolidates the negative stereotypes they already have in mind and they think, oh yeah, I'm not good at math. That's how I'm made up, you know? So it could discourage students from pursuing further STEM education. So that sums up the first part of the talk. Any questions so far? Okay, so now we see that if we just apply vanilla machine learning algorithms, there can be substantial racial bias in math education. And now let's look at how we can build a more fair machine learning algorithm. And yes, the high school data set is public, but the middle school data set is from my collaborators and not public yet. Any other questions? Okay. For the second part is the paper we're going to present at yours this year. It was selected for oral presentation, and we have 3 co-authors, and this is us staying on the Zoom course from 2 a.m. to 7 a.m. before the deadline. Okay, so as we saw in the previous example, this is the typical pipeline of learning. So we have a data set and we train a classifier and we saw that there's a substantial gap between the 2 groups. So the goal here is to build a classifier that can ensure some kind of fairness metrics. And there are actually a lot of fair classification algorithms out there since this field has been very popular field of research. This is definitely not the complete list of papers in this topic. But just like any other machine learning research is, these research papers depend heavily on the data sets we use to evaluate the algorithm. And those data sets that I commonly use in this field are Compass, Adult, and Credit. And the problem with these data sets is that they're pretty small. They contain only thousands or tens of thousands of samples. They're simple. They only have 10 to 20 features. And also some of them are really outdated. I think Adult and Credit are more than 20 years old. So because algorithms are developed using these data sets, there are limitations of existing fair machine learning algorithms. So first, they only benchmark on small data sets, and we don't know how well they're going to perform if we have millions of samples. And because most of these data sets have only binary labels, these algorithms only work for binary prediction problems. and also binary sensitive group attributes like male or female or black or white. And to summarize the main contributions of this work, we proposed an algorithm called fair projection, which can be used for any number of classes and also any number of protected groups. And we also tested on a data set that has more than 1 million samples, and we also show that it can converge very fast on a big data set. Okay, and let me give you the core idea behind fair projection. The idea is based on information projection. So let me just explain what that is. So we have a probabilistic classifier, H-based, we already trained. And what we want to do is we want to find another classifier, H-opt, that is in this set of true fair classifiers. So all of the classifiers in here satisfy the fair constraints we want to satisfy. And what we want to do, and another great thing is that a lot of fairness constraints we talked about, such as equalized odds or statistical parity, can be written as linear constraints in this probability space. And then what we want to do is we want to find a classifier in this set that is as close as possible to the original classifier so that we don't sacrifice a lot of accuracy achieved here. So then we want to minimize the distance, and the distance metric we use is called F divergence. This might not be like so familiar to you, but it's a general class of distance metric between two probability distributions. And depending on how we choose F, this can be KL divergence, or this can also be cross entropy, and it can be also many other things. So the goal here is to find a new classifier H that minimizes this F divergence distance within the set F. And the really cool thing about information projection is that this actually has been studied in the information theory community since the 1970s. C-Star studied information projection a lot. And the really cool thing is if you look at this optimization problem, you might feel like, how do you even solve this? And it turns out that it actually has a closed form solution when the constraints are linear. And one of the first authors, Wael Agambi, he adapted C-Star's results to find a closed form solution for our problem. And this is the solution of the optimization problem. And if you look at this, the new classifier H-opt is simply a scaled version of the original classifier H-base. So all we have to do is we have the classifier we already trained, and we have to just multiply this constant factor. So the only remaining problem now is to find this constant factor, and this P function is an explicit function, so we just have to find lambda star. And lambda star can be found through solving a strongly convex optimization problem. So because this is the simply multiplying scalar here is a model agnostic post-processing method that can be applied to any class of base classifiers. And to solve for lambda star, to solve that strongly convex optimization problem, we use ADMM algorithm. I'm not going to go into any detail of this optimization problem, but one thing I want to highlight is that to solve this problem, we have to iterate through all of the training samples. So when n is large, the number of samples is large, this can be really slow, but all of the steps that have to go through all the training samples can easily be parallelized. So this can be parallelized on GPUs, which leads to really high performance of our algorithm. And we also, in the paper, we also show some convergence guarantees that this algorithm can converge in all of log n steps, and is the number of training samples, and all of n log n time. All right, now I'm going to go into our experimental results. Before I go into the results, any questions in the idea or the optimization?
In the algorithm, what is the role of the function Q?
Function Q.
The variable large Q. And in the fourth line,
Uh,
two.
it's,
I mean, yeah, 2 lines of, yeah, 7.
I think it's used here. So G defines the fairness constraints, depending on whether you use statutory or equalized laws, we have different G. And I think Q just encodes that fairness constraint. It's just the identity metric plus that G metrics. Thank you for the question. Any other question? Okay. All right. So we have this pretty simple idea and a great like optimization algorithm. And let's see how well it performs. So we benchmarked on 4 different data sets. And this is result on binary classification. So even though our algorithm is really general and it can kind of multi-class problems, but the problem is there aren't that many methods out there we can compare against once we go beyond the binary classification. So we first show comparison results on binary classification, and then I'm going to show our results of multi-class predictions. So ENEM, and this is high school longitudinal study data set, the same data set I used earlier, and 2 more traditional data sets. And this black star is the base classifier without any kind of fairness intervention. And we benchmark against 5 different fair classification methods. And the y-axis is the accuracy, and the x-axis is mean equalized odds. So we are basically measuring the difference in false positive rate and false negative rate between 2 groups. So we want this mean equalized odds to be as small as possible. So being on the left side is good fairness, and being higher means a higher accuracy. So we want the higher curve as high curve as possible. And if you look at these 4 results, we can see that the our fair projection performs consistently well in all 4 data sets. It's very competitive. And I would say only this orange curve, which is reduction method, performs consistently well, almost as well as our fair projection in all 4 data sets. And I want to emphasize that this ENEM data set is a new data set we introduced in this paper. This one has 1.4 million samples, and it's collected from Brazil. It's collected from Brazilian university entrance exams, and it contains student demographic information and their grades in this exam. And if we compare these 2 methods, reduction methods and our fair projection algorithm that perform very competitively in all of the 4 data sets, reduction methods work really well, but it requires retraining classifier multiple times, so it's very slow. If you look at the runtime analysis on this big data set, reduction data set requires more than 200 minutes, and our fair projection algorithm is more than 20 times faster than the reduction method. And lastly, I want to show multi-class prediction results using fair projection. So there's only one method that has publicly available code to do multi-class classification, which was adversarial debiasing paper. And it's the same graph, y-axis is accuracy and the x-axis is fairness. And you can see that fair projection, our method has higher curve, which means we have better accuracy fairness trade-off. And also we can see that our curve extends farther to the left side, which means that we can achieve much better fairness compared to adversarial debiasing method. Yes.
Your baseline is only the projection based methods, or you compare with other like processing?
That's a great question. So in here, so reduction approach is actually in processing method. And I think all the other ones equalize the rejection, and these ones are post-processing methods. So we wanted to compare against mostly post-processing method because that's more like fair comparison. But we included reduction because reduction, and in our experience and in the literature, reduction is usually the most competitive method. It performs really well in a lot of data sets. So we just wanted to compare with reductions, even though it's in processing method. Any other questions? Yes.
프로세싱 메서드라고 했었는데 그 알고리즘에서 찾는 게 그러니까 웨이팅을 바꿔줄 수 있는 펑션인데 람다를 쓰는 거 같은데
맞아요. So here we are kind of re-scoring the score function we have, and then you can pick up this as the weight. And this is the function, but the only variable we don't know is lambda. So we try to find lambda through this algorithm and plug that in, and then we do that postmark. Yes.
there be any also computational issue if you apply this to like, high dimensional data, which is vision based? Because do you suffer more complexity or is it?
I think compared to, so let's say we compare with reductions approach. Obviously the computation complexity will go up when we use high dimensional data. But in reductions approach, they have to train multiple classifiers iteratively. So if they, let's say, if we have to train a complicated model for like high dimensional data such as image, reduction has to do that multiple times. So if the one training takes like an hour, it could take like 20 to like 100 hours just to do that retraining. But for us, I think solving this optimization problem, I don't think it should have like high dependence on the dimension.
Regarding that, the equation, closed form solution, in the multi-class case, I know if it's a binary classification, the output of the model is just scalar, so it can just multiply to scale. But in multi-class, it's like probability softness. So how do you, is it like inner product or is it?
Oh, so that's a
The
good.
equation is on the previous page.
So this C is actually a class. So if we have multiple classes, like you said,
Then one element of that probability.
right? So we have a vector, and this is one element. Exactly. Yes.
And then the summation over C, is that always one?
Yes. Yes. It's always one. Yes.
Okay, good, thank you.
So if it's like n class problem, then we just find n minus one of them, and the last one is on that can be found. Any other questions? Okay. All right. So that was our work on fair projection. So to give you a summary, by using this idea of information projection, we developed really generate and efficient fair post-processing algorithm called fair projection that satisfies a lot of these features we want in a fair learning algorithm. And if you want to know more details, this is the QR code to our archive paper. And again, we're going to present this work at NeurIPS this year. So if you're going to NeurIPS, I'll see you all at New Orleans. Okay, and the last part is about fairness in missing values. So what we realized was that just considering fairness when we're training a classifier is not enough, because fairness issues can actually arise much before training a classifier. And I'll tell you more about this soon. And this is a joint work with Powell and Flavia at Harvard, and we presented this work at AAAI this year. Okay, so to recap, fair machine learning literature, we define group fairness metrics like this. And if you look at these performance metrics between two groups, we want the difference to be as small as possible. And a lot of these fair machine learning literature focuses on training a model that reduces this difference at the model training stage. And we use like clean and curated data sets that don't contain any missing values. But in reality, in real world data sets, they're not as clean and they contain a lot of missing values. And usually data scientists do some kind of data pre-processing to deal with the missing values. And then we come to this stage. But the model function fairness issues that could arise here, right? And this problem was actually motivated by the middle school and high school data sets I was working with because they contain a lot of missing values. And more importantly, different groups have different missing patterns. So this is an example of data missing rate statistics in the high school data sets. And I'm showing data missing rates for white, Asian, and Black, Hispanic, Native American students. And you can see that, so these are three example variables. And in all of these variables, Black, Hispanic, and Native American students have higher missing rates. And for some variables, like secondary caregivers, higher education, this difference is as high as 15%. And missing values are really everywhere. I would say almost all real-world data sets contain some kind of missing values. For instance, in survey data sets, people just don't want to answer some questions because they think it's sensitive information, or in electronic health record data, there are missing values because not everyone takes the same set of medical tests. And in police reports, police officers don't always fill in all the details in the report, so there are missing values. And we're making important decisions with this data, such as education-related decisions, medical decisions, and bail decisions. And it is really important to understand if we can train a fair model, even when there exists disparate missing patterns across the groups. Okay, so let's look at what exactly we do in the data pre-processing stage to deal with missing values. So what people usually do is the process called data imputation, in which we fill in the missing values with a new value. So it could be mean imputation, so we can just impute mean values in all of the missing entries, or we can do median imputation, or we can do something more sophisticated like nearest neighbor imputation. And this data imputation and learning with missing values actually has a really extensive literature, and also learning a fair model has a lot of papers in recent years. But these two together have not gained a lot of attention in the community. So at the time we are writing this paper, we only found two relevant works. So Fernando et al. Did some kind of experimental study on how different imputation methods we use here could impact the final prediction fairness. And Wang and Singh in 2021, they proposed a reweighing approach that assigns lower weights to data points that have a lot of missing values to achieve better fairness. But as an information theorist, we pose a more fundamental question, which is that, is it sufficient to impute first and then simply apply a fair learning algorithm on the imputed data? In other words, if we consider all of these steps that come before data training stage as a black box, and just take whatever fair learning algorithm and apply it here, is that enough to guarantee fairness in the final outcome? Does this question make sense? Okay. All right. So towards answering these questions, we make theoretical contribution, and we also propose a new method. So in the theoretical analysis, we show different risks of this joint process of data imputation and model training. And each theorem shows different risks. So first theorem says that the imputation method itself can have biased performance. So what we mean by biased performance here means that if we just apply, let's say like mean imputation algorithm, then it could have high accuracy in one group and low accuracy in another group. And the second theorem says that bias can arise from mismatched imputation methods between training and testing time. So let me explain this a little bit more. So when a company releases a machine learning model for some kind of prediction, it releases the model, and then users have to now apply that model to do their prediction task. And the data they collect could have missing values. but they have no information on what kind of imputation method the company used when they trained the model. So without that information, us as the user have to choose whatever imputation method and then apply the prediction algorithm we got from the company. And there can be the mismatch between what they use and what we are going to use. And sometimes disclosing imputation method like disclosing mean imputation and disclosing the mean value of the training data could be compromising user privacy. So the company might not be able to disclose the imputation method at all. So this is a practical problem that could happen in the real world. And the last theorem is kind of fundamental information theoretic results, like impossibility results, that says that there is no universally fair imputation method for different downstream learning tasks. So let's say we found the optimal imputation method that has the best accuracy variance trade-off for logistic regression. But if we apply that for different downstream tasks like training a random forest or training a deep neural network, then it could have very poor performance. So this is basically showing that if we have a separate imputation process without the knowledge of the downstream task, it is always somewhat suboptimal. So inspired by these results, we proposed a new method called fair MIP forest, which integrates data imputation and training into one algorithm. It actually doesn't really require imputation at all. And if you look at this accuracy variance trade-off, we can see that fair MIP forest performs much better than doing this direct imputation applying fair learning method. Yes.
Regarding theorem one, you said even the mean imputation may have different effect
Right.
on the group. Is that because of the variance of those feature value? I mean, mean imputation doesn't have any algorithm just computes.
Right.
So why we have different bias?
Yes, I think variance is one reason, and the other reason could be the mean of one group and the other group can be different. And if one group has like higher population, then the overall mean value is skewed towards this group, and then that mean imputation won't be as accurate for the minority group.
And minor question, theorem 3, that sounds similar to no free lunch theorem in machine learning.
It does, yes.
Okay. Is
Yeah.
there any similarity in the
True.
kind of interpretation or in the derivation? No.
I don't know how no freelance theorem is, you're right, but for our theorem, we just have like a one counter example that shows. Yeah. Any other questions? Okay. Then I go into the algorithm in a little bit more detail. So to overcome the limitation of decoupled imputation and training, we propose an integrated approach based on decision trees. And a great thing about using decision trees is that we don't actually have to do imputation. We can use data missingness as an attribute. So it's some technical missingness in attribute. So instead of filling in missing values before training, we just leave missing values as they are. And we just have to decide at each branch where we want to send the missing value. So for instance, at this branch 0, we are using feature 2 to do splitting, and when feature 2 is missing, we just send all of that to the left branch. And at this branch, we are using feature 0, and when feature 0 is missing, then we're just sending all of them to the right branch, and so on. And then, so we can use this to circumvent doing the imputation. And the second question is then how do we integrate fairness constraints in decision tree training? And for that, we are also using the idea that was proposed in the literature by Age et al. So they propose mixed integer program formulation of training a decision tree. So the usual way of training a decision tree is just doing some kind of greedy optimization at each branch. So we can really specify the exact loss function we want to optimize. So to have the loss function that has the user loss function we have and the fairness regularizer, we use this formulation of integer program. So using this, we can write decision tree training as an integer program, and we can have an explicit loss function. And this fairness regularizer can be statistical parity, equalize all the accuracy parity, all of those metrics we already saw. And training a decision tree now can be formulated as binary variables in this integer program. And but this formulation didn't have any the data missingness in mind, so we are integrating this idea and putting this missingness into this optimization program and make it a little bit bigger optimization program. Okay, so now we want to evaluate how well this algorithm works. So what we want to compare is doing this imputation plus fair learning and fair MIP forest. And we use 3 different data sets, complex adult and high school data set. And for fair learning, we use 3 different methods: disparate mistreatment, reduction approach, and equalize post processing. And for this imputation, we use 2 different kinds of imputation: mean imputation and median imputation. And again, now you should be familiar with this accuracy fairness trade-off graph. So we want the higher curve that has good accuracy and good fairness. You can see that for different imputation methods and different baseline methods, compared to all of them, fair MIP for us has much better performance. Any questions? Yes.
이 인디비주얼 페어니스를 고려하는 거랑 좀 비슷해 보이는데 내부적인 구조가 관련되거나
So the question is, it's somewhat similar to like individual fairness related methods. Is there any connections? I don't know. So in what sense do you see the similarity to individual fairness?
실제에서는 하는 법에 해결을 할 때 보통 인별적으로 해서 이제 다양한 값들에 대해서 페어니스 프레딕션이 어떻게 되는지 비교하는 식으로 접근할 수도 있으니까 그 부분이 인디비주얼 페어니스가 관련성으로 보시면
Yeah, yes, I think you're absolutely correct. I think there's like a lot of relation to individual fairness because of the mean imputation, but also two individuals could be kind of similar with just observed variables, but the missing values can be very different. Then those 2 individuals should get different treatments because in truth, they are like pretty far away data points, but because they have a lot of missing values, they look like similar individuals and they might get similar treatment, which is actually not there. So I think this problem actually has a lot of connection to individual fairness, and we kind of want to extend our work to individual fairness as well. So I think that's an important future work.
실험에서 데이터에 대한 미싱러닝을 보시고
Oh, that's a great question. So the question is how do we generate missing values here? So for high school data set, they already contain missing values, so we didn't have to generate artificial data missingness. But for complex and adult data sets, we artificially generated missing values. And so we ran experiments on different combinations of data missing probabilities. So we wanted to have different missing patterns for a group. So we want to by these different missing values, the only thing we wanted to change was different missing rates per group. So maybe black people have missing rate of 0.1 and white people might have missing rate of 0.3. So we iterated through this kind of different combinations and found the combination that had the highest bias or highest performance difference at the baseline. Because if the baseline already performs really well for both groups, then there is not much bias we can correct in the fairness intervention. So we generated the missing patterns that show the highest discrimination, if that makes sense. Yeah. Any other questions? Okay, so So as I said earlier, this topic of fairness and missing values is really new. Not many people have looked at this issue a lot, so there are a lot of open problems. So, for instance, there is no such thing as fair imputation method. Like, how do we design an imputation method itself that can be fair? That's a wide open question. And also, our method only works for decision trees, but can we do something similar, like integrated approach for other machine learning models, such as neural network? It's another open question. And in practice, people do multiple imputation, which means that imputing one instead of imputing one value, we can suggest many different values that could be for the missing entry. So that's multiple imputation, and how do we apply these ideas for multiple imputation? And lastly, as someone asked in the audience, how can we extend this to other fairness metrics such as individual fairness or preference-based fairness and so on? Okay, so let me check how much time. So I don't have much time. So let me just quickly sum up. So in the first part, we show how vanilla machine learning algorithms could discriminate students. And in the second part, we show how information theoretic tools can be used to build a fairness in machine learning classification. And the last part, we kind of use information theoretic thinking and blueprints to understand in missing values. So just to give a few words, I worked a lot on reliability challenges in machine metrics during my PhD, and to build reliable distributed computing systems, I researched something called coded computing, which integrates coding theory into large-scale distributed computing. And looking forward, I want to continue working on both reliability and in machine and human metrics. I'm not going to go into any details here, but I'm still working on these like fair machine learning issues and also coded computing for building secure and private machine learning systems. But lastly, I want to mention that I am recruiting students and postdocs at beautiful UC Santa Barbara. This is our campus. And we have 2 Nobel Prize winners in the department. And we have really strong faculty in information theory, machine learning, and statistics in both ECE and computer science department. And we have really strong basic science programs like physics, chemistry, and biology, all top 10. And we have very collaborated environment. And this is our department building. So it's right by the beach. So this is the view I have when I walk out of the office. This is literally just when I walk out of my office. And we don't just have the ocean, like on the other side, we have the mountains. So it's like Tetan YouTube, very beautiful environment. And we don't just have the nature, we also have very deep Spanish history and culture. So this is, we have fiesta every year that celebrates Spanish culture and history at the courthouse. And if you can't believe how beautiful it is, another evidence is that a lot of famous people live in Santa Barbara, like Oprah Winfrey, Prince Harry, and Meghan Markle. They live in Santa Barbara, and the Kardashians have their vacation house in Santa Barbara. And that must mean something, right? When rich people live somewhere, there must be a reason. And another big perk of living in Santa Barbara is it's only 1.5 hours away from Koreatown, Los Angeles. So if you miss the Korean food, you can always drive down there in 1.5 hours. So if you're interested in all of these research questions, feel free to reach out to me via email here. And I want to thank all of my collaborators again, and thank you so much for listening.
For students and postdocs in Santa Barbara.
Great question. I'll do no comment.
Okay, any more questions from?
근데 말씀 주신 방법들이 어떤 스트리트에 대해서 페어한지를 신는 페어한 이제 모델을 만드는 쪽이었는데, 예를 들어서 뭐 나이, 뭐 성별, 뭐 머리색, 인종 이런 게 다 들어가 있는데, 그 같은 경우는 혹시 어떤 요소가 제일 페어함을 저하시키는데 영향을 주는지 찾는 방법 같은 게 혹시 있을까요?
That's a great question. So the question is, there's a lot of attributes that could lead to discrimination in the prediction results, and can we find an attribute that contributed the most to the discrimination? And we tried to do that kind of analysis, when we did the, like, education data analysis. And what we tried to do was just to get rid of, one feature and see whether the discrimination changes, or getting rid of a group of, features, and then see if the, discrimination reduces. And it was not very straightforward to do that analysis because we had like more than 200 features. And even if we get rid of like one feature, there are a lot of features that are highly correlated to that feature. So the discrimination didn't really reduce by a lot. And also we can do kind of feature inference kind of thing and see, which feature is most correlated with the sensitive attributes like race or gender, and we want to get rid of those features that are highly correlated with the sensitive attribute. But even if we do feature importance analysis, because of this problem of having a lot of highly correlated features, it doesn't give you like very accurate information on which feature is most relevant. So I think it is generally an open question how to do that kind of analysis. That's a great question though. Thank you.
There are about 20 participants online. Maybe you can ask them, ask if they have any questions.
Is there any questions online?
Probably not. In the meantime, I'll ask a kind of broad question about the research trend. You talked about various methods about the fair machine learning. Is there like kind of approach to combine that with maybe explainability, other important topics of machine learning?
I think that's a great question. I think it's also related to the question you asked, like whether we can explain why discrimination or bias happens. And I think it's really important to have like explainability. But I don't think there's a lot of work that does exactly that. I would say there's some research on algorithmic recourse, which is not exactly the same, but maybe somewhat related. So what algorithmic recourse papers do is they want to give, when you receive a prediction, they want to give you a suggestion on what you can do differently to get a different prediction. So let's say your loan was denied, and we want to tell you that, oh, if you pay off these many debts, or if you increase your income by this much, then you can be approved for this loan later. So this can give you some kind of information on how this decision was made. But this fair explainability, I don't think there's a lot of work in it, but also like fairness and privacy, they're like correlated, because if we want to have a lot of data, then the decision we make based on those data can be more unfair because now we don't have sufficient data to make it fair and so on, but there could be some kind of trade-off. I think that's also another like big open question, and I think there's a lot of exciting open questions in the internet. Yes, question.
일반적으로 예전에 테이블 데이터를 가지고 세연 시장을 하다가 최근에 이제 대체제가 없어서 셀러웨이 같은 걸 쓰고 있었던 걸로 알고 있는데, 그 방법론적인 측면에서 이런 이미지 데이터에 대한 거랑 테이블 데이터에 대한 거랑 구분해서 다양한.
I think so the question is for like image data sets or not non-tabular data sets, if we have to use different methods. For instance, our fair projection methods would work as well on image data sets because we can use any kind of base classifier. And I think it would be the same for most post-processing methods, because once we have the classifier, we can just do the simple post-processing, but maybe for in-processing method, that might be more dependent on the classifier itself. But I don't think we have to use fundamental different tool for non-tabular data sets. But I think the only difference is that because for small tabular data sets we use, just like random forest or logistic regression, they already perform pretty well, so we don't really have to use deep neural networks. But for that you can just use different Bayes classifier. Is there a question there? No.
Let's thank the speaker again. Great talk. 자, 그럼 오늘 세미나를 마치도록 하겠습니다. 감사합니다.